Hello everyone, and welcome to my talk on modular monoliths with the Akka model. I'm going to split this into three sections. So the first section, modular monoliths, I'm going to try and make the case that modular monoliths are the way to go. Next I'll talk about Akka and introduce the Akka model. And then at the end we'll try and bring it all together and talk a little bit about evolving architecture. So, modular monoliths. I'll start with a bit of a historical viewpoint. Around 2011, the term microservice was coined. That was a conference in Italy. A lot of large companies came together, and we found that they were building very kind of similar architectures, loosely inspired by Unix and Linux. So smaller processes which do one thing very well that you can kind of compose and combine to do more complex things. Then, about halfway through 2012, Netflix started making noise and started making more and more noise right through into kind of 2016, 2017, when they were giving these really impressive talks about running thousands of microservices in parallel, and it all sounded very cool. Then mid-2015, Martin Fowler started saying, a lot of the successful microservice stories started with a monolith. And then 2016, the article deluge begins. Everyone who's written a blog starts writing about microservices, and many people who've never written a blog before decide, now's the time. I'm going to write about microservices.
Sorry, Matt, you share it's the wrong window being shared. Sharing your IDE, unfortunately. Sorry about that.
Sure. I don't know how to change that. I'm just sharing my screen.
Really?
Yeah. I think that's where Google Hangouts is. Okay, sure, sorry. So yeah, then by the end of 2017, the programming zeitgeist completely flooded. Everyone's talking about microservices, and if you're not doing it, you feel a little bit left out. Then by Christmas 2017, the sales teams learned the word. I was working on a monolith at the time, but somehow all the customers thought we were building microservices. And then coming towards the end of 2018, people really started talking about monolith first and making modular monoliths. And then just as that kind of started to ramp up, blockchain arrived and everyone started talking about that instead. Now we're at the kind of beginning of 2019, and a lot of the people who are thinking about monolith first here are finishing projects or getting to the point where they're hitting these scaling problems and starting to get some case studies out there, of which I have one. Beginning in 2018, we had a plan, and it worked, and we are successfully scaling, and it's been easier than I hoped. So I'll be sharing some of that towards the end of the presentation. So the spaghetti monolith. I think the term monolith, whenever you hear it, you immediately think spaghetti. In fact, the term monolith itself is kind of pejorative. Like, if you hear somebody say, "Oh yeah, they're just building a great big monolith," you think, "Oh God," because that's what we think. I'm going to use this example throughout with, say, an e-commerce platform where you're buying something online, and you've got these separate domains of products, users, inventory, baskets, and tax. And when you think of a monolith, you think of all these things just being a mess inside, and all these separate concerns overlapping and it being difficult to deal with. And even if it's not spaghetti code, even if you're kind of well ordered, you're following some kind of pattern, it's still a little bit more difficult to reason about, because if I change something up here, it's a little difficult to reason about what the impact's going to be, down here. But what could be simpler than this over here, right? With just straight strands, change something up there. It's all nice and clean and simple, which leads us to our impression of microservice, just clear. It's just straight. It's nice. Everything's easy. But the reality is, if you're, instead of building this monolith spaghetti, we're going to build these nice, clean microservices. But the reality is, if you were going to set out and build a monolith that looks like that, you're going to build microservices like that, right? Except this is an order of magnitude worse, because these are all network boundaries now. So you've introduced, an orders of magnitude more latency, and you've distributed your data, and querying is harder. But monoliths can be modular too. So to any of you into domain-driven design, I think this is what they call bounded context. You can absolutely build a monolith in a modular way. In C#, this might be C# projects. In Java, you've got packages. I think there's modules on the roadmap. Every language has namespacing to some extent. Enable this. So one of my key points here is that monoliths are more malleable, which is really important at the start of a project. So this, take a look at this graph for a minute. You'll notice there aren't any units or scales because there's no data backing this up, but it is nevertheless true, I promise. Where at the start of a project, your uncertainty is really low. Even if you think you know the domain well, after you start building, concepts that you think were the same turn out to be different, or there's a lot more work involved, and vice versa. Find out a lot way after you start building. So experimentation is easier in a monolith. A common, there's an example here. So if you had a microservice for inventory and baskets, you might find that these share a lot of data, or there's a lot of communication going on between the two. And a common pattern here, if they're both small and you think actually these aren't really separate ideas, a common operation is to just merge the two, which is easy in a monolith because you're just refactoring in application. And likewise, I think the opposite is more often true as well, is concepts which you think are the same, you end up getting very large and then you're splitting. Which, again, we're talking about the start of a project. So, yeah, monolith first. It's easy to refactor, which is important at the start of a project. It gives you the time and the space to figure out the domain, which is really what you're doing then. It's one deployment. I can't understate this enough. That I've dealt with a team before that probably spent the first month or so trying to configure Kubernetes and getting deployments up. And then a month later, you ask them something about the domain and they don't know yet. They are easy to test. I know testing microservices is a solved problem, but you can't. At some point, someone's got to get all the microservices together and check that they work. And reporting, as always, it's a simple solution when your data's not distributed, so you can get first version out there quickly. And all the previous bullet points, basically just this last bullet point, which is focus on the product initially. This is a lot of my job really, because so I work at a place called JISC in the R&D department, and a lot of what we do is trying to spin up new products quickly, and lots of them, and find out if they're even going to work and fail quickly. So it's very important to focus on the product rather than the tech at the start. I am saying monolith first. I know the next talk's from OVO, so there's probably a lot of OVO microservices guys in. I'm not saying microservices never. They are good. Microservices scale really well, but in particular, I think they scale organizations really well. Having 40 people working on a monolith is not fun. You won't get 40 people to agree on how they want to build it. So you end up with extra tiers of management, and tiers and tiers and tiers, and the people actually building the application end up with very little autonomy, which is generally bad. Whereas if you're at that kind of scale where you've got 40 people, you can build, you can split them up into teams of 4 and have 10 microservices, and that all works fairly nicely. But who starts a project with 40 people? So for this first part, point I'm trying to make is just that monoliths can be modular. Stop thinking of monolith as like a bad thing. But monoliths are better at the start, and yes, microservices are good for when you've large teams and you've got a lot of people trying to work on one product. So part 2, I'm going to now introduce Akka. So Akka is a library which started for Scala. It's really nice in Scala, but it's being JVM based, it's It's also got a Java API, which is really nice and also quite widely used. A few years back, there was a C# port, which is now also pretty mature and pretty good. So in any of these languages, I would recommend it. Basic premise is you create your application and you start up an actor system. The actor system hosts your actors. There's one. And actors just run code. That's all they do. They have a low memory footprint, so it's more than reasonable to run one actor per user, potentially. You can run thousands of them, and it's fine. And non-blocking, so when they're not actually running code, they're not consuming a thread. They're not consuming any CPU. Basic premises, they send messages to each other. They might send commands, please do something, or share data. They might ask for something and then receive a response. Parents supervise children, so an actor can create child actors, which it supervises. This kind of introduces another really great thing that Akka can do, which is it's got a great solution to fault tolerance. If you have dangerous operations like processing a file or accessing a database, you can push that out into a child actor, and then if for some reason that fails, the parent can have some kind of supervision plan. So say it crashes, you can create another actor in its place to start the process again. Or maybe you just want to forget about it, log it, and create a new actor, which is then going to move on to the next thing. And it contains that fault into that actor, which you can dispose of if you need to, and it doesn't bring the whole actor system down. And they, again, will communicate by sending messages to each other. You have this, and children can have children of their own, and you have this big branching structure. I think it actually works. It's quite an intuitive model to build applications with, because there's a lot of parallels to the real world as well. So you could think of this as similar to an organization structure where maybe you've got the CEO at the top who's technically responsible for everything. He's delegating out, and they're delegating out, and they're delegating out. And then probably down at the bottom you've got actors which are actually doing stuff like I/O. And as a last point there, I'd say it's idiomatic to kind of send messages down the chain rather than trying to skip levels. So you might declare that you want a piece of work done, send a message down, and then that might send the actor you've sent it to will then be responsible for passing on various bits of work further down the branches. Key benefits are concurrency. With this model, for free, if you've built something with multiple different actors, they can be running in parallel, doing completely different things. It's easy concurrency. Asynchronicity, that's more, I suppose, around performance, so not consuming our thread. And if you ask another actor for something, you don't consume a thread, you just sit there and wait, and then the actor system will handle starting that actor up again when the response has arrived. So yeah, very, very performant as well. And the fault tolerance that I talked about. These are some key benefits, I think. So now I will show you some code, but a quick show of hands first. Who thinks they can understand C# syntax? Raise your hands. Good, everyone. And who kind of understands Scala syntax? Raise your hand. Okay, not very many. Okay, let's start with some C# then. All right. So this is that large enough? No. I've also gone white so you can see it. So that's about as basic as an actor as you can get. The only dependency I've got here is Akka. I've inherited receive actor. There's a couple of different types of actors, don't need to worry about them. And then in my constructor, I've registered a receive method. So if I receive a message of type get user by ID, I will do this processing with it. I'll take that message and I will, do whatever database access logic, for example, that I might want to do. And then I know the sender, I know who sent me the message, and I'm just going to whoever sent it to me, I'm going to respond with that data that they've asked for. One key thing to note here as well is this is done by type. So you're sending messages around, and it's generally based on the type of the message that you've sent. They're really nice to unit test as well. I think they make you think about tests in the right way. So when you're building an actor, you are just thinking about that API. You don't, it helps you not think about the implementation because you're just thinking, I've got this actor, what messages am I going to send to it, and what messages do I want back? And that's your API surface. So anyone who's into TDD, it's nice for that as well. And with C#, one thing to really be aware of is you are sending, when you're sending data or messages between actors, it's going across a thread. So the data needs to be immutable. You'll see this a lot. So a read-only property with the data coming in through the constructor. Because it's a standard concurrency problem where if you've got data being mutated on one thread and on another thread, you've got a problem. And some other languages, so in like Kotlin, they've got data classes, if anybody knows that, or Scala, case classes. I think in the upcoming version of Java, they've got data classes as well. So you'll have that on the Java API. So I am going to show some Scala code now. Apologies to everyone. How can I scan up? Is that readable or is that going to be too small? Too small. Let me just figure out how I can. Does anyone know where Zoom is on this? Sorry? Under view? Sorry. Yeah. Cool. Ah, cool. That's still quite small. Yeah, that's fine. That's fine. We'll deal with it. So that's what an immutable class looks like in Scala. It's the same thing as you saw before. So if we were to look at the same code, as before, we've got our user actor down here doing the same thing. Essentially, because Scala has pattern matching, again, it's based on the type that the actor has received. Just sending the same message. But then, we're going to start adding more code to this kind of thing. These things grow. And a lot of this talk is about scaling and growing an application. So then, if we were to, let's look at another example. So I was saying about pulling dangerous operations down out into child actors because they might fail. So let's say I've got a few different database reads. I might pull that down into a child actor and have that parent actor supervising it. And again, because everything's routing and being picked up based on type, we can have our messages that we're sending around just, say, inheriting a trait or an interface in C#, route things around that way. And then when they get to the bottom, based on the actual type it is, that's where you can have your implementation of, okay, this is get product by ID as opposed to just get products. And then, it provides a lot of nice inbuilt ways of doing things. So instead of creating one child actor, say, you might decide to create a pool of child actors and set them to do round robin. So that's, you might struggle to see it, but that's what this line here does, where I can just say send it to a pool of actors, and the actor system handles which actor it's going to go to. So I might have a pool of 5 identical actors. The first message goes to the first actor, second to the second, third, and so on. They just take it in turns. There's a bunch of different ways you can do this. You can do it by shortest inbox or whatever you want. This allows you to do multiple things in parallel, and it frees up that parent actor to then just move on to the next piece of work it's doing. There's a lot in here to allow you to scale and tune as well. So let's jump back into the presentation. Okay. So just to summarize that section on Akka, actors are just things that run some code and they send messages to each other. That might be a query, so asking for something, or it might just be sending a piece of data. So those of you into messaging patterns, there's all sorts of clever things you can do here. So we accept command query setups or publishing events. There's a lot of benefits to this because messaging patterns in general will, if you look into them, there's lots of nice ways to scale out there. Easy way of scaling to efficient multi-threading, which is still a problem that's in a lot of languages, I think. And it carries you up that curve. So that curve I showed you earlier, this will get you a long way up it before you need to start worrying about breaking things up. Which brings me to part 3, evolving the architecture. One of the things I'm doing at work at the moment is building something called the GIST, Technical Maturity Model. Basic premise is trying to classify how mature a product is and providing some kind of vocabulary for business people and technical people to talk about it. So at level 0, that might just be something which it's a prototype running on your machine, and you might have shown it to someone. Hopefully it's in source control. Level 1, it might be deployed to an environment, and you've got some unit tests around some of the core business rules. Level 2, for somewhere like JISC, you're thinking about hitting AA accessibility and making sure that your database is getting backed up, stuff like that. By level 3, you're thinking about things like auto-scaling and networking. Level 4, you're maybe automating that accessibility testing you were doing earlier, and you're thinking about zero downtime deployments. And level 5, I haven't quite figured out what could be that good. Yes, part of the point here is about bringing less mature products to be more mature and giving them ideas of what to think about. But the other side of this is, if you're just starting a project, don't worry about the stuff down here at level 5. If you're just starting a project, why are you worried about doing zero downtime deployments when you haven't got a client yet, or that kind of thing? It's about accepting where you are. I think that a lot of the time as engineers, we are really interested in the stuff down here and the real technical challenges, but I would put to you that perhaps the real challenge is building something up here which you can evolve and carry through to down here. Every time you pick up, you start on a new application and you think, right, I'm going to throw this away and start again, this is rubbish. That is a failure to have evolved it up. And there's a lot of good reasons why that might happen. If it's a legacy Perl application which your granddad built, that might be a good reason why you can't evolve it, but it's still nevertheless a failure to evolve. So there's a few different mindsets I want to talk about. First is microservices are end goal, so let's start there. That is really, to me, starting way at the end. And I think that is probably wrong. We talked a bit about that in part 1. But the other thing you see quite a lot, that I'm not advocating for, is we don't need to architect because we're agile. I've definitely worked like that before as well at points, because you had to, where a ticket comes in, you just do what's required for that feature and nothing more, and yeah, that feature's done, and then your architecture is just like emergent by chance, by the order that you've done the tickets in, or what was asked for at the time, and you just end up with an application. That is probably wrong. Let's be honest, a lot of people get away with it, and get away with it for a very long time, but nevertheless, probably wrong. So where does that leave us? Well, continuous architecting. If you're working in some kind of like agile process, in the same way we expect business people to be, a couple of months ahead, gathering requirements, and potentially have a big long backlog of stuff for next year, or whatever. We should also be architecting ahead. We should be thinking about where we want the application to go, have a plan, so we don't hit the point where we're like, actually we need to take 6 months and rebuild it, sorry. So yeah, not restarting. We have to do it, we've all done it, I've done it a lot. But you can plan ahead and build in options for yourself in the future and avoid it. But still build to the current quality requirements. Don't jump straight ahead in it. The end goal. And as I said, planning for evolution and building in that flexibility from the start. And Akka is one path. That's why I'm showing Akka. This is how we've done it on a couple of pretty large projects where we found that Akka is a great fit for a modular monolith and beyond. It provides a really great evolution path. Part of that is that I know this is a bit of a difficult one to explain, but it encourages you to think about messaging, which then breaks down quite well. It encourages you to loosely couple things. And parallelism and asynchronicity are easy, which are really important kind of through that middle of the curve. You don't need to start thinking about splitting up into microservices just to start getting a bit more parallelism on tasks with heavier loads. And then at the end, straightforward to split out to microservices. I might skip this bit just because size. So I'm going to go through the evolution steps that we found worked. First off, you might start with a script just to prove something. And then you might wrap that in an actor and you get some stuff for free from that, so there's the fault tolerance and things like that. And then start splitting it out, moving dangerous operations down into child actors. And all your general nice code quality stuff, so splitting stuff up so the classes stay small and manageable. And with that, you get your parallelism and concurrency for free with it. Then you can start thinking about splitting the domain up and getting that right. And you'll probably be on this step for quite a while. We were, as we split things up and then merged them again and got things wrong and created microservices inside it that we thought we needed and then just didn't, or thought it was going to be a lot of work and then turned out the users weren't that bothered about it, or business changed direction. So you can stay on that step for quite a long time. And then eventually you hit the point where you are splitting out the microservices. And at that point you're at your end goal. So just to reiterate again, I'm advocating for evolving rather than picking an end goal and then picking a route to get there, as opposed to picking an end goal and then trying to build that. And this is a way that we found worked for us. I'm going to give a side note on data storage because I think that is probably the most difficult parts of this. We've typically gone with a single database for this, but you can just have multiple schemas. So in SQL Server, you tend to just dump everything in like DBO dot or Postgres in public. You create multiple schemas for the different areas of your domain, or what you think they are, and possibly multiple users. I've tried this where potentially different parts of a monolith are using different database users with restricted permissions. So you can try and enforce that separation of data. And you can still have all your nice foreign key constraints, but those areas don't need to know about the other tables. And I'm going to say it again, it's easy to hit your reporting requirements, which, to begin with, it's typically just trying to run a script and dump out an Excel spreadsheet. I will concede that the database stuff is trickier to evolve, but I think it's even worse if you start at the position of splitting your data up. So just to summarize this third section, which is think about evolving your architecture. And Akka enables a really good path. We found that it works and works really well. And that's kind of my go-to now for starting new projects. And yeah, a little bit early, but any questions? Yes. Hello.
I've got a little bit of experience back from a few years ago,
Mhm.
and I really liked it.
Mm.
But I'm interested to know how you evolved from using Akka messaging, which has got its own internal routing
Mm.
and that sort of stuff, breaking that into microservices. So do the messages route across microservices quite well?
Yeah.
To then install another mechanism like
Yeah.
JSON.
Yeah, really good question here. So typically the way we tend to build stuff is we'll have each of these kind of actor structures, each of these trees will be topped by a REST interface. So then when you want to start breaking one section out into a microservice, you just need to make sure that that top actor, that the whole API surface is covered by REST interface. Pull that package out with a REST interface, and then go through and update all your usages to point to this REST interface. And then you can actually start pulling it out. And yeah. So just to reiterate the steps there, you cover the API with a REST interface, deploy it separately, test it, then update the monolith to point at that microservice. So we found it.
You can cut the active systems
Mm.
them and then cluster them, and
So-
that's automatic, so you don't have to even to do REST.
So I think that's you're talking about there. Isn't Akka clustering something slightly different? It's Akka remote, I think you mean, maybe. There's another library called Akka remote, which allows actor systems on different machines to communicate with each other. The reason why I would probably not recommend that path is just because a nice REST interface is much more interoperable, whereas something like Akka remote is very it's much more constrained. You're then stuck with actor system.
Yeah, I think between microservices, you want the REST API, pretty much that is the way microservices tend to.
Yes, exactly. Yep. Yeah. Because inevitably someone's going to rewrite it in Go or something.
Whenever I hear anyone saying a framework gives me concurrency and you just speak for free and all that, I always think,
Yeah.
at some point you hit an edge case where you pay the cost. Could you talk a bit about if you've hit any of these problems or things that occur where you've got something the framework hasn't quite thought of and what the problem
Yeah.
is?
So just to repeat the question, which was when you hear about getting concurrency for free, it's always sounds a bit of a dubious claim because it is a difficult problem. When I and have we hit any problems? It's a good question. I would say when I say you get it for free, you still have to write code. Is I guess the real answer there, which is when you start introducing things like order, which is always difficult with concurrency. If you want to do things with concurrency but then try and maintain order throughout, you've got to code that up. It's when you start adding those kind of additional problems. Things like supervision, you've still got to declare how you want it to work. It's just an easier framework to do so in. That's my answer to that.
I just ask what my experience was that all the actors are single threaded, so access to the local variables are limited obviously to one from that, so that's something there. And also if you've got lots of concurrent transactions that are operating on different transactions, you can almost create a transaction and actor for a transaction as well. That was my experience.
Yeah. It also does start to get more difficult if you start putting a lot of state in your actors. I would still recommend following the standard practice of putting all your state in backing services and having a stateless application. Yeah. Hi. Yep.
One of the points on one of your slides was something like parallelism and asynchronism are easy.
In this, yeah.
What do you mean by that? Because in one sense, it's easy because you can create it very easily, but the consequences aren't necessarily easy to do.
Mm-hmm. So the question there was parallelism and asynchronicity being easy, but potentially the consequences of them aren't easy to deal with. Akka gives you a lot of tools with which to deal with it, and the actor system itself will help manage a lot of stuff. So one problem may be, let's say you've got a lot of actors running and you send a message to one. So say you're hitting high load, messages can just build up in the queues, and the actor system will handle running an actor and giving it a message when it's got the resources to do so. So you don't end up with a lot of resource issues from it. And obviously you still need to leverage, if you want to do good asynchronous like I/O, you still need a nice asynchronous I/O library. So yeah, does that kind of answer the question?
Yeah, that's what I understand. What it was.
Yep.
Right through.
Do you tend to hit any problems when you start splitting out your actors into separate services that aren't on the same host, say? And in fact, actually, that's another question. When you start with a small system, is it all an actor system on the same host?
Yeah. So the question is around actor systems and splitting them across hosts. So yeah, really, really good question. Because the actors in general consume very little memory, so you can run that same actor system. This is what I mean about keeping it stateless. Running that same actor system on multiple applications behind a load balancer. So you can still scale on resources and fault tolerance that way, but rather than initially, whilst it's still a monolith, trying to run parts of the actor system on one machine and parts of it on another, as we kind of discussed a few minutes ago, there is Akka cluster and Akka remote, which can let you do those things, but they are much more complicated, and that's not the evolution path I'm recommending. I'm recommending keeping it all as one monolith, deploying it multiple times, and then when you want to start breaking things off, you put a REST interface in the middle. So it's like it's like any other two services communicating.
I think that was the second question. In some sense, the first question was when you're not having an exact replica with it being stateless, and you actually have different aspects, and maybe do you have the case where you have one of your actors will need to call a different actor? I mean, maybe this is just the same with microservices, really, but when you've got an actor having to make a call to another actor rather than through REST
Okay.
onto the actor system, does that cause any problems?
Okay. So in application, so you're saying, so sorry, but it was the question in a monolith, one actor calling another part of the actor system via REST.
In the monolith, I suppose you've got your actors call each other.
Yes,
in
exactly.
the same host.
Yep.
When you break it up, they might be calling each other via REST.
Correct.
Or perhaps even via REST on multiple hosts.
Yeah.
At that point.
Yeah.
Does that cause problems?
No. So at that point, you would follow your standard pattern where. So this is the problem of potentially if you've got actors calling some other microservice via REST. If you're doing network stuff, that's often something that you would push out into a child actor and follow that same pattern of if it fails, you can have the parent actor do whatever supervision it needs to. Yeah. And as far as it knows, you're following your standard microservice pattern where it doesn't know anything about what it's calling. This is why I suggest not Akka remote, but to do REST, because it doesn't know about what it's calling. It's just following an interface which is hopefully well designed and interacting with that. Does that answer the question?
Yeah.
Yeah.
I think your answer is it's not really been a problem.
Yeah. It's not.
In terms of following a design with the actor model, is it sort of, in terms of like a best practice, as it were, would you kind of put each actor as a single responsibility, or do you have it in the sense of like an actor can perform multiple tasks, but it just watches various messages? Like if it gets to the point, for example, where it's getting a bit too monolithic, is that when you sort of say, right, now I'm going to take it down into the child?
Yeah.
To the point where you genuinely do have actors just doing one particular thing.
Yep. Yeah, really good question. So the question there was about actors and should they have a single responsibility, or potentially would you have an actor consuming potentially a lot of other code and a lot of other objects and doing a lot of different things. So potentially at the start of the project you might have an actor that's doing, yes, quite a lot, but I would recommend you start splitting things out. The reason why is because as you start to split things out, that's when you start almost by accident designing something that's more concurrent and things like that. And it becomes easy to reason about as well. You will see out in the wild applications built both ways, so actors that are potentially that are basically backed by a whole bunch of, say, object-oriented code. So quite a large object-oriented code base, but they're just kind of using this they're using one actor to just run it. I would advise to go a bit more heavy on using actors as your unit of work, and yeah, trying to follow, to some extent, single responsibility. Yeah. Somebody else had a question as well, didn't they? Okay, I think that's everyone. Yeah, thank you very much.